All right, problem number 2 on the calculator part of the review says a ball is dropped from a height of 10 meters. Each time the ball drops, it rebounds 7/10 the distance that it drops. What is the total distance the ball travels? Okay, so to do this, we're definitely going to need to use a geometric series, but let's just talk about like what happens really with this. So let's think about this. Let's try ourselves a little visual. A ball is dropped from a height of 10 meters. So before anything happens, we have this ball that is sitting 10 meters off the ground. Cool? And I'm going to do this. I'm going to put my column of n down beneath this for terms, my term number. So think about this. A ball is dropped from a height of 10 meters. Each time the ball drops, it rebounds 7/10 the distance that it drops. So if this ball is dropping down and then bouncing back up, it's only going to bounce back up 7/10 the distance that it dropped. So mathematically, what we're saying is 7/10 times that original height, which was 10, equals the distance that it drops, which in this case is easy to do. It's just 7. So when the ball has dropped out of your hand, bounces, hits the ground, bounces back up, the highest it goes after that first bounce is 7 meters. You with me? So I'm going to let n stand for the number of bounces. So if you think about that first height, 10, well, I'm going to call that n equals 0 because it didn't actually bounce yet. And then after one bounce, it was 7 meters. So now after 2 bounces, it's going to be 7 times 7/10, which is 49/10, which is 4.9. So after it bounces for the second time and it goes back up, it reaches a height of only 4.9 meters. Now, this pattern is going to continue forever until the ball is essentially on the ground. Now, in the real world, we know that, yeah, the ball is going to be on the ground. But mathematically, the way we represent this is we do an infinite series because the ball is going to continue to get closer and closer to the ground, and eventually we're not going to know the difference between a really, really ridiculously small fraction and actually touching the ground. So if you think about this geometrically, each time the ball bounces, its previous height is multiplied by 7/10. So 7/10 is our common ratio. Now here's where you got to be careful with the way you think about this. Remember that we said n is going to represent the height after, n, the term number, represents after that many bounces. So 7 meters is the height after one bounce. 3.43 meters is the height after 3 bounces. The problem is 10 is the height before any bounces. So when there are 0 bounces, the height is 10. Now the reason this is a problem is because if you think about the path of this ball, say it's going to start from its highest point, bounce down, and also, side note, we're saying that this ball is dropping straight up and down. I can't represent that with this graphic. That's why it looks like it's going side to side, but assume I just drop it from straight up and down so there's not any like sideways motion we have to worry about. So you drop it from its height of 10, goes down, hits the ground, bounces back up to 7 meters. That's its second max height. Then it's going to fall back down, hit the ground, bounce back up, and it's only going to go 4.9. It's going to bounce back down, hit the ground, go back up, and it's only going to go 3.43, etc., 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 forever. Now, the important piece to notice here is that for every single bounce, you actually get double the distance that it bounces because it bounces up and then it drops back down that same distance. So I am going to separate this part of my calculation with, I'm going to separate that from the original bouncing of, or the original height of 10 meters. The reason I'm doing that is because we want to find the total distance that the ball travels, and to do that we're going to use an infinite series, and we're going to write it like this. Our first term of this infinite series, I'm sorry, let me move that. I'm going to put that right here. If we do our infinite series like normal, n equals 1 up to infinity, this is geometric, so geometric is going to be our first term. Well, our first term is 7, if we go by term number 1, times our common ratio, which is 7/10 to the power of n minus 1. And again, check to make sure it works. 1 is our first n value we're plugging in, so we're going to get 7/10 to the power of 0, so that's 1. So we get 7 as our first term there. And that's what we wanted. Okay, now the reason I'm writing it like this is because of what we said. Every time for each of these in this summation, we actually need double the value because of the whole bouncing up and dropping down thing. So I'm going to represent that by putting a coefficient of 2 in front of the value of the sum. That's kind of cool. On top of that, don't forget, we did not include that initial 10 meters in this calculation. So I'm going to say, how about if we do 10 plus that? And now this awesomely little cool equation mathematically represents what we're trying to say. And remember, since this is a geometric series, we can use our summation formula, which is the infinite sum is equal to the first term divided by 1 minus the common ratio. So we're going to get 10 plus 2 times our first term, which is 7. So I'm actually just going to write that like this, 2 times 7 over, which I'm just going to pretend, again, 2 times 7 is 14, over 1 minus our ratio, which is 7/10. And so we have 10 plus 14 over 1 minus 7/10 is 3/10. So we can continue to simplify this, although this is a calculator question, so you could use your calculator also. But whatever, it's good to practice this. So let's keep going. 10 plus 14 over 3/10 is the same as 10 plus 14 times 10 over 3. So we're going to get 10 plus 140 divided by 3. And I cheated. I got tired of playing the game. 140 divided by 3 is 46 and 2/3. So we're going to get, if you add 10 to that, 56 and 2/3. So that should be the total distance, meters, that the ball travels.